I now call to order the Society's 2,452nd meeting in the 150th year since its founding on March 13th, 1871. Good evening, everyone. My name is Larry Milstein. I'm the president of PSW, one of the oldest scientific societies of Washington, D.C., committed to providing a forum to further scientific understanding and inquiry. Welcome to our members, guests, and friends to tonight's lecture by Olivier Guyon. Tonight's meeting is being held via Zoom, partly because our speaker is in Hawaii at work on the Subaru telescope's adaptive optics, and partly because of COVID. As of now, we are planning to have the next meeting in person, but this will depend on COVID and on the measures instituted by government authorities and the Cosmos Club. The venue will be posted to the website and highlighted in the announcements that will be sent before the lecture. Please check the website frequently for updates. We will be live streaming all meetings to YouTube for our remote audience to enjoy and to ask questions in the YouTube chat box. And final versions of the live stream recordings will be posted to the PSW YouTube and Vimeo channels, where they will be permanently available for everyone to view without charge. The Society is grateful for the support of our sponsors. Please join me in thanking the sponsors of the 2021-2022 lecture series for their support, the Policy Studies Organization in cooperation with the American Public University, and a generous donor who's asked to remain anonymous. Thank you, sponsors. I am pleased to announce the following new members. Eric Samuel, a physicist and principal engineer with Signal Systems Corporation, broadly interested in physics, particularly instrumental methods of analysis, such as NMR and ESR, and signal processing, who learned of PSW from a family member and from the PSW website. Rita Caldwell, a micro and molecular biologist, distinguished university professor at the University of Maryland, College Park, broadly interested in science, with particular interests in microbial ecology, metagenomics, molecular and biotechnology, who's known of PSW for many years and attended many lectures. Bill Goodwood, an event and video producer with Future View Productions, and a musician interested in a range of science topics, especially evolution, genetics, cosmology, and physics, who learned of PSW when I contacted his company for information about video and sound production. Now, tonight's speaker, Olivier Guyon, is already a member, having given a talk last fall. We'll learn more about some of his interests in even more detail from tonight's lecture. We welcome them all to membership. If you're not a member and would like to join PSW or support the Society, you can do so through the PSW website using the blue Join button on the upper right-hand corner of the homepage. We welcome new members and we appreciate donations. Recording Secretary James Heelan will now read the minutes of the 2,451st meeting and the lecture by Sean Andrews on planet formation.
Good evening, everyone. On December 17th, 2021, from the Pebble Auditorium at the Cosmos Club in Washington, D.C., President Larry Milstein called the 2,451st meeting of the Society to order at 8:03 p.m. Eastern Standard Time. He welcomed new members, and the recording secretary read the minutes of the previous meeting. President Milstein then introduced to the speaker for the evening, Sean Andrews, astrophysicist for the Smithsonian Astrophysical Observatory, part of the Harvard-Smithsonian Center for Astrophysics. His lecture was titled Planet Formation. NASA's exoplanet archive, as of the lecture, included more than 4,800 confirmed measurements of exoplanets and planets in our solar system. NASA's data is compiled using transit observations, Doppler method, microlensing, and direct imaging. Andrews said the data is currently skewed toward large planets and planets at close distance due to present observational limitations. Still, the available data shows great planetary diversity, which Andrews attributes to planetary formation processes. Since the mid-20th century, scientists have believed that indirect evidence established the existence of protoplanetary disks. Then, in the 1990s, the Hubble Space Telescope captured images from the Orion Nebula, confirming that belief. The classical model of planet formation has long held that first, over the course of several 100,000 years, cold, dense molecular clouds collapsed into flat, rotating disks and created stars. Material in disks then began to disperse and formed planets within the first million years. In this classical model, planets formed by smooth gas disks seeded with planetesimals that then accreted until they became large enough to pull in their own atmosphere and form planets. Andrews said this core accretion model of planet formation isn't efficient enough to be accurate. An alternative model is Pebble Accretion, by which the solids on a disk are different sizes, and the smaller pebble masses accrete quickly onto planetesimal seeds. This model lacks the core accretion model's timescale problem, but still suffers from needing to explain accretion and gas disks. Accretion is difficult to explain because collision energy tends to be destructive rather than constructive, and when particles embedded in gas disks, they start to aerodynamically decouple from the flow of the disk. Andrews explained how at 100 astronomical units, small particles would lose 10% of their orbital distance, and large particles would drift inward toward their star. This radial drift stunts particle growth in smooth disks at around 1 centimeter. Structured gas disks with velocity deviations would converge migration of pebbles into traps with local concentrations with high solids to gas ratios. Such disks do not suffer the limitations of smooth disks and theoretically would lead to planet formation. But the fluid dynamical models that actually create the necessary pressure substructures are small. Then in 2012, an international partnership commissioned the Atacama Large Millimeter Submillimeter Array, or ALMA, with 54 12-meter dishes and 10 7-meter dishes that work in concert to give 30 milliarcsecond resolution. ALMA has produced groundbreaking images of diverse planetary systems with different morphologies. Every system seen so far has shown pressure perturbations, including on the scales of our solar system. The most common morphologies look like concentric rings with gaps between them. Strong, non-axisymmetric features are less common, and large-scale spiral patterns are rare. Mixed modes are indicative of complex hydrodynamics. The high prevalence of disk substructures implies universal processes. The sizes and scalings of these substructures are broadly consistent with expectations of magnetohydrodynamic instabilities in numerical simulations of the disk fluid, and are promising venues for efficient planet formation. Andrews explained those conclusions with recently captured images, highlighting a specific bona fide example of planet-disk interaction. He said there was a plan for the James Webb Space Telescope and an upgraded ALMA to investigate further questions. The speaker then answered questions from the online viewing audience and from those present. After the question and answer period, President Milstein thanked the speaker, made the usual housekeeping announcements, and invited guests to join the society. President Milstein adjourned the meeting at 9:42 p.m. The temperature in Washington, D.C., 14 degrees Celsius. The weather, cloudy. The number attending live and on the PSW Science YouTube stream, 71. Cumulative views on the PSW Science YouTube and Vimeo channels, 304. Respectfully submitted, James Heelan, Recording Secretary.
Thank you, James. Send any comments on the minutes to Corresponding Secretary Robin Taylor at correspondingsec@psw.org. That's correspondingsec@pswscience.org. The minutes will be posted to the website in due course, corrected or revised as advisable in light of any comments submitted. We now turn to tonight's lecture on extreme adaptive optics. It's my pleasure to introduce tonight's speaker, Olivier Guyon. Olivier is an astronomer at the Steward Observatory and professor in the Department of Astronomy at the University of Arizona. He also is affiliated professor with the Astrobiology Center of the Japanese National Institutes of Natural Sciences and served as extreme adaptive optics project scientist for the Subaru telescope, and also as a member of the Magellan Extreme AO development team. Currently, Olivier is developing high contrast imaging techniques for current and future ground and space-based telescopes, particularly innovative techniques for detecting and characterizing extrasolar planets. He developed a highly efficient optical device to mask light from a star while preserving light from planets around it. And he is now leading the Coronagraph Extreme Adaptive Optics Group at the Subaru Telescope, which I think you may hear about tonight. He is an author on over 169 refereed publications and more than 486 non-refereed publications. Among other honors and awards, he is a MacArthur Fellow, a recipient of a Presidential Early Career Award for Scientists and Engineers, and a Guinier Young Researcher Awardee of the French Society of Physics. Olivier earned his undergraduate degree at the École Normale Supérieure of Paris and his PhD in astronomy at the University of Paris. All questions will be fielded after the lecture during a Q&A session. Olivier, the screen is yours.
Thank you, Larry. It's great to be back. So in the fall, I gave a lecture on adaptive optics as an introduction of adaptive optics. And tonight, I'm going to go a little bit more technical, a little deeper into how adaptive optics works, and especially talking about the type of adaptive optics that I'm most familiar with, so-called extreme adaptive optics, which is really pushing at adaptive optics to its ultimate performance. Without any other introduction, let's go forward. And first, I'd like to remind ourselves of what is adaptive optics. When we build large telescopes and we look at stars from ground-based large telescopes, the images stop getting sharper with larger telescope size. We actually get into a limit, which is due to our own atmosphere. Essentially, everything is blurry. Adaptive optics is a technique to unblur images. And so it works as such. There are essentially three main components. There is a mirror, which can change shape, a deformable mirror. So the goal of that mirror is to exactly undo the optical aberrations that the atmosphere imprinted on the beam. To do this, we need a sensor, a waveform sensor, a sensor that can measure what are those deformations. So we know what signals to send to the mirror so that they can get corrected. And there needs to be a computer, a control system that processes the images or the data that are taken by the waveform sensor, and then computes the signals to apply to the mirror that needs to compensate them. And when we do all this, we end up with an image where we've largely undone the blurring of the atmosphere, and we recover the ultimate sort of theoretical performance of the telescope. So there are many types of adaptive optic system, and they can be defined by maybe two quantities. The first one is the field of view. So that's the horizontal axis here. Some adaptive optic systems are made to work over a very narrow sort of field of view, looking at one single object. Others are aimed at delivering sharp image of large portion of the sky. And then the other axis is the quality, the wavefront error, the quality of the residual quality of the optical beam. The hardest part of this diagram is the lower right. That's when we want exquisite quality, optical quality over a wide field of view. I'm going to be talking about the lower left part of this diagram, which is called extreme adaptive optics. And extreme adaptive optics is essentially what we refer to as adaptive optic systems that are optimized not to work over a wide field of view, but to deliver the ultimate best performance over a very small field of view. And the reason the scientific driver to do this is to image exoplanets. So we want to image planets around other stars. And the reason we really need to do this is so that we can study their spectra, we can isolate their light, put it in a spectrograph, and identify signs of life, or at least habitable environments. Here I'm showing a spectra of our own planet, Earth, which was cleverly taken not by flying a satellite looking back at Earth, but looking at the moon and looking at the Earth shine, the part of the moon that's illuminated by Earth. And in that spectra, we can identify life. We can see that there is water, oxygen. There is the sky is blue, which is due to our atmosphere scattering sunlight. We can also see the vegetation red edge. So the sign of vegetation is the color essentially of our planet is impacted by vegetation. These are the measurements we want to be able to take for other planets. Now it's difficult because Earth is much smaller than, much fainter than our sun, and the same ratio of contrast applies to habitable planets around other stars. So the technical challenge is to image a very faint source of light that's very close to a considerably brighter star. And this is why we need adaptive optics. And this contrast, which is very challenging, is the reason we need to push adaptive optics to its ultimate performance. And that's why this type of adaptive optics is referred to as extreme adaptive optics. So an extreme adaptive optic system it requires a few components. The first one is actually a high contrast imaging system requires a few components. The first one is an extreme adaptive optic system that corrects atmospheric turbulence. The second one is a chronograph. It's an optical mask essentially to remove starlight, but preserve light from sources that are around the star, such as planets. And then we need a lot of techniques and image processing to pull out the signals from the planet. Today, I'm only going to talk about the first one, the extreme adaptive optics component of this challenge. So let's start with nuts and bolts. What does it take to build an extreme adaptive optic system to image exoplanets? Well, the first thing we need is a large telescope in a good site. So here I'm going to use the Subaru Telescope Extreme Adaptive Optic System, SKEXEO, as the example for this talk. And this is a picture of the telescope. It's located in Hawaii, and you notice that there is snow, which means that it's pretty high up. So it's at 14,000 feet, 4,200 meter elevation, which is great because that puts the telescope above most of the clouds and a large fraction of the atmosphere. So there are clear skies usually above the telescope, and not too many clouds, and as little atmosphere as possible, so that the image is as sharp as possible even before we start deploying adaptive optics. And this is a fairly large, one of the large telescopes. There are multiple telescopes in the sort of 10-meter range. This Subaru telescope is 8.2 meters. It's one of the large telescopes that is currently in operation. You may have heard, and that has been covered in previous lectures in PSW, that there are larger telescopes currently in development, and so we're all, of course, very impatient to see this telescope get on sky. So if we look inside the dome, that's what the telescope looks like. So you see here we're looking from the top of the telescope, and we see in the bottom of this tube, we see the mirror. This is the main component of the telescope. For Subaru telescope, it's 8.2 meter across. So light comes from the top. It goes through this top ring, which is in the foreground in this picture, and then it hits the primary mirror in the back. This mirror is curved, So it focuses light back towards the top ring, but this time the beam is very narrow and it hits the center of the top ring. And then there's multiple possibilities. We can have a camera at the top ring, which is actually what is shown in this picture, or we can have a mirror that sends the light back down. And let me show you the arrow. And then the light would travel from the secondary mirror back to another mirror here, which is called the tertiary mirror. And then it goes off on one of the two sides. And the instrument, the extreme adaptive optics instrument on Subaru, is located on the side of the telescope. So light bounces on these three mirrors and then gets to our instrument. And so if you look on the right here, this is a cartoon representation of the telescope. We were looking at a picture from the top, seeing the top ring and the primary mirror in the bottom here. But our instrument is located on the side of the telescope. It's located on a platform, which is actually fairly large. The area of this platform exceeds the collecting area of the primary mirror. So it's a fairly large platform. And this is where our extreme adaptive optics instrumentation is located. If we look at the footprint of that platform, so here the light comes from the bottom, from the telescope. There is an initial layer of adaptive optics correction, and then there is our finer correction of adaptive optics, the extreme AO layer that provides exquisite wavefront control and also a removed starlight. This is, so if we look at a picture of the instrument on the platform, this is what it looks like. So here, to situate ourselves, the telescope is on the right behind this big wall, so we cannot see the telescope. But the telescope sends us a beam through this ring on the on the right side of the picture. The light first goes through this fairly large black box. This is the first layer of adaptive optics correction. And then there's a second layer of adaptive correction, the extreme adaptive optics layer, which is in this central part of the image. And on the outside, we see various cameras and instruments that capture the light from exoplanets. The red one is working in the near infrared, for example. So if we look at a sort of diagram of what's inside all of this, the extreme AO instrument, it's fairly complicated. There's lots of optics, lots of sensors, cameras, stage, because there are multiple functions to be performed. One of them is to provide a very high quality correction. Another one is to remove starlight. And then there are several instruments that have to be fed by all this system. So let me zoom in a little bit. I'm going to mostly focus on what happens in two optical benches. The lower bench is this big box here, and the top bench is above here. There are lots of optics, which is actually fairly common for such systems, partially because there's a lot of functions to be performed, but also because the beam is quite small. We're not trying to have a wide field of view, so we can cram a lot of things together in a small volume. The things I want to draw attention to, the main components of all of this, is this little thing here. It's called deformable mirror. It is the mirror that will, at very high speed, compensate for wavefront aberrations, for atmospheric turbulence. And then everything that's in the middle of this picture, where my arrow is to remove starlight. And then, so that's the lower bench. And then on the upper bench, the only thing we're going to talk about today is this part here. That is the wavefront sensor. That's what measures starlight at high speed and very high precision, to be able to compute what is it that we should do. We should have the deformable mirror do to basically undo atmospheric turbulence. And in between all of this, not shown in this diagram, is of course a fairly powerful computer to run this at high speed. So this is what it really looks like in terms of hardware. The lower bench, which we call the infrared bench, is here, and the upper bench, the visible bench, is up here. Again, consistently with the previous slide, you can see that there are lots of optics, and none of them are very large. The beam is actually quite small. This is what defines a lot of this system, the extreme AO system. Is the field of view is very small, so we can get away with taking this huge telescope beam, which is 8 meters, and compress it to essentially about a centimeter or half an inch. And most of the instrument essentially is dealing with this very small beam. So zooming in on some of the components, the deformable mirror, which is one of the main components of the system, is here. So this is in the sort of central part of this picture. We're looking at it a little bit from above here. It's very small. The active part of that mirror is only 20 millimeter in diameter. Yet we have 2,000 independent actuators, so essentially push-pull actuators that can move the continuous reflective surface of this mirror. And we can do that about 10,000 times per second. So this is a very critical component. It physically looks very small, but it's one of the most essential component of the system. So in this picture, light comes from the telescope, from actually the top part, goes through this small hole, and then it goes to the bottom part of this picture. There's a mirror just outside of the picture in the bottom part that then sends light back to this mirror. Then light is reflected from that mirror and travels straight down to the next part of the system, which is the one that is removing starlight. On its way to this optics, the beam is actually reflected. There is a plate of glass that will reflect the visible light and transmit the infrared light. The infrared light is used to take the images of the planet. The visible light is reflected to this periscope, which sends it up, sends the light up to what we call the top bench, and that's where our wavefront sensor is located, the device, the camera that will at very high speed measure wavefront aberrations. So a few other views of the system. You can see optics that are gold color. It's not just by taste. It's actually a gold coating, and gold is the preferred optical coating to reflect infrared light very efficiently. So all of the infrared optics have mirrors that are of this color. They are actually of a thin layer of gold. You see multiple big wheels like this. Those are wheels that rotate, where we can select different masks or optical components. So here we're looking from the back of the system. The deformable mirror, small deformable mirror, is at the top here. So you can see that light will travel through these wheels, and those wheels are holding optical masks that are removing starlight. Another view of the system. Again, we see the mirror gold coated and multiple wheels. I think you get the idea. It's actually quite dense, lots of optics. And again, I'd like to stress that this is all fundamentally due to the fact that our field of view is very small, so we can get away with very small optics. Here is another view, different wheels. Some of them are of different shapes so that the beam can travel through them. We've gotten very good at packing a lot of optics in a small volume. Here is another view. Here we actually see a camera on the left, one of the sensing camera that's used for alignment. So if we sort of look at this on a block diagram level, this is what the whole thing looks like. We have the telescope collecting light. We have an initial adaptive optic system. We call it the facility adaptive optics that does the initial correction of the atmosphere. And then we have the fine correction that happens in the central part of this diagram with a faster deformable mirror, a chronograph to remove starlight, and then we have instrument on the outside. One unique and defining feature of extreme adaptive optic system is that they usually have multiple wavefront sensors that some of them can work simultaneously, and some of them work out of the final image itself, which is kind of unusual for any other adaptive optic system. This is why if you count the wavefront sensors in this diagram, you find that there's a few dedicated wavefront sensor. There's 5 of them, but there are those purple boxes that are both science instruments and also can act as wavefront sensors. They can inform the system on the state of the optical aberrations. This is how we observe. So as probably all of you know, professional astronomers don't spend time looking at light through an eyepiece anymore. Those days are long gone. We are observing, running the instrument from computers. So as an example, at night, this is an example of several of the team members are located in a control room next to the telescope at 14,000 feet. And then several of us, including myself, I think I was on travel on that particular observing run, connecting through Zoom, through remote connection. So I talked about the hardware, and let's talk a little bit about the software and the algorithms that power all of this. Adaptive optics control usually consists of this algorithm. We have an input, which is a wavefront sensor input. So the wavefront sensor is looking at starlight, and it is telling us essentially what is wrong about the optical beam, what optical aberrations have been imprinted by the atmosphere. This usually uses a very high-speed sensitive camera looking at starlight in some way that makes it easy to recover what are the optical aberrations. So this measurement is collected usually at very high speed. For extreme adaptive optics, it's typically from 2,000 to 4,000 times per second. And what we do is we multiply it by a matrix. So we do a linear operation, a matrix vector multiply, to derive a control signal, an output, which we send to the correcting element, the deformable mirror. So usually the algorithm consists of this. We have an input that gets multiplied by what we call a control matrix and creates an output. And we run this loop at very high speed, typically a few kilohertz. So we really leverage this linear relationship, and we actually build our systems to have that relationship between what the deformable mirror is doing and what the wavefront sensor is seeing. So we can write this as a linear equation. A is the wavefront sensor measurement. B is the comments that are sent on the deformable mirror, and there is a linear relationship between the two, which we can represent as a matrix multiplication. And the first step is that we need to figure out what this matrix is, and we can actually measure this matrix. We can send. Usually we do this in the daytime with the artificial source, a laser. We can send comments to the DM. So we basically move the mirror, and then we record what is the wavefront sensor seeing in response to those comments. That allows us to build this response matrix, essentially element by element. So we populate it. We basically learn by actuating the mirror what is the relationship, linear relationship between the mirror motion and the sensor. This is what it looks like on our system. On the left, I'm showing you this response matrix. So this is what the sensor sees. This is how the sensor image changes for every actuator of the DM being poked. On the right is the reference. So on the right is essentially what is the sensor going to see if we don't have any error. So just let's focus on the right for now. The right is essentially the wavefront sensor. It's a camera, and it's looking at the beam. It's kind of weird because you can see 4 copies of the beam, and that's on purpose. And I'll show you why we do this. We have 4 copies of the telescope beam. If there is no optical aberration, that's exactly what the camera sees. The image will be static, and we will see exactly that. Now, if we push one of the actuator, we will see essentially light up in each of those 4 copies of the beam. And this is what you see on the left. And so on the left, we're basically scanning from actuator to actuator. You can see this little spot moving, and each of this image, each of these frames is essentially the change that the wavefront sensor experiences when we push one actuator of the DM. And we can measure that very efficiently. It's actually fairly easy. We set the camera to capture the image, which is on the right here. And then we just walk through every actuator and we push it, and we measure the corresponding change in the image, which is what I'm displaying on the left. So it's fairly easy to make that measurement. So this is not, we're not quite done. We don't really have exactly what we need to run the adaptive optics loop, because what we've done is we've measured what we call the response matrix. This is the matrix that if you multiply it by the DM perturbation, the DM command, the deformable mirror essentially shape, you will get the signal that the sensor measures. But we need to go the other way. When we actually try to compensate for atmospheric turbulence, we have a measurement that the sensor gets us, and we need to figure out what is the deformable mirror command that would cancel that measurement. So we need to go the other way. We need to essentially invert our response matrix into what we call a control matrix, so that we can, every time we get a new wavefront sensor measurement, we can multiply it by this control matrix to get a command to be applied on the DM. And that is the matrix that we will enter in the computer to do this multiply matrix vector multiply operations at high speed. There are a few techniques to compute that control matrix. We need to be a little bit careful in the way we numerically invert the response matrix to ensure stability and optimal performance. We usually use a technique called singular value decomposition, which gives us access to individual modes that we can finely tune for optimal performance. So everything I described so far is not unique to extreme adaptive optics. I described to you essentially how to run an adaptive optics loop, but that applies to any adaptive optics loop. Extreme adaptive optics is special in a few ways. The first is high speed. We need to run faster than a conventional adaptive optics system. We need to run typically faster than 2 kilohertz. And we need to do that because ultimately we want a very exquisitely good correction, which means we can't be lagging behind the atmospheric turbulence very much. The atmospheric turbulence is constantly changing, pushed by wind. And if we want to match it very well, to correct it very well, we need to measure it at high speed. Otherwise, we're going to be lagging behind. The other defining feature of an extreme adaptive optics system is a large number of control modes. We want to have very fine level of control, which means we need a deformable mirror with lots of actuators, and we need a wavefront sensor with lots of pixels. So just the dimensionality of the system, number of input measurement and number of output control channels is very big, which is a computational challenge. If you combine the requirement for high speed and large number of control modes, you quickly find yourself with a computational challenge that becomes quite significant. So we do actually work a lot on our computer, on our real-time computers, making sure that we get very fast computers and the software is very efficient. And we also need a very high accuracy and precision. Not only we need to measure the wavefront at high speed with a large number of pixels essentially, but we need that measurement to be very accurate and precise. Those three requirements combined really drive us to have a very efficient wavefront sensing scheme. We need a sensor that's very good and very efficient at converting light into a measurement. And as a reminder, even though we're looking at stars that are not so faint, when we go very, very fast with lots of pixels, there's not so much light per measurement. And so we need to be very, very wise and very efficient about the way we use light. So when we work on extreme adaptive optics system, we really try to optimize our efficiency for measurement of optical aberrations. So one thing that comes into play is the first thing that comes into play is the choice of wavelength. What color are we going to use to make that measurement? And there are a few considerations. If we go to a bluer color, the wavelength of light gets smaller, which actually helps us to get a better, stronger measurement. But it depends on the type of the stars we look at, because if we go too far to the blue, maybe the star, especially if it's a red star, doesn't have much light. We like to go into the red because we tend to also have a more reliable measurements, but the wavelength is longer, so we don't get as much of a sort of leverage. one challenge when going to the red is we need to share light with the science camera. So we need to be a little bit strategic with what part of the light do we use for measuring the wavefront error, but what part of the light do we need to keep for measuring the planet, essentially. And so the answer, the sweet spot, depends on the star we look at, the spectral type of the star. So this is, astronomers have kind of obscure ways to define the color of stars using letters, but we can look at the temperature of the star, the equivalent, the effective temperature of the star. The very hot stars are blue. The fainter, the redder stars are cooler. And depending on the type of the star, we'll find that we want to maximize that number on the right part of the table. We'll find that we need to jump to different colors, essentially, to make the best measurement of the starlight for wavefront sensing. Typically, we like to work in the visible light, and when the stars get very red, then we can work in the near-infrared light. We also need, in addition to what I just described, which is let's go where there is the most possible, the largest amount of light to make the measurement, we need to be very efficient in the way we use that light. So there are various types of wavefront sensors, various optical ways to convert the starlight, the beam essentially, into a signal that we can use. And the one we use on our system is called a pyramid wavefront sensor. It's called a pyramid because it actually does have a pyramid. It's a glass pyramid. Light from the telescope is focused on the tip of the pyramid, and that pyramid splits the beam into four. One thing that happens is it's fairly easy to visualize that if the telescope is slightly mispointed, the light will not hit the tip of the pyramid. It will go into one of the four faces, and then only one of those four copies of the beam will be illuminated. So it gives us, using this little experiment, we already see that we have a very sensitive way to measure where the starlight is pointed relative to the tip of the pyramid. This is shown here. Those are simulations. If you move the star into this quadrant of the pyramid, so you miss the tip, basically one of the four images is very strongly illuminated, the others are dark. If the light is hitting exactly the tip of the pyramid, the four images are roughly equally lit up. And then this extends to higher orders like focus, astigmatism. We can actually measure a lot more by looking at exactly how the light is distributed in each of these four images. These sensors happen to be very sensitive, and so that's why we use it. So here I'm showing you a real on-sky snapshot of what our instrument sees. And I'm showing you three different cameras at exactly the same time. The pyramid camera, the one that measures starlight to measure wavefront errors, to measure the optical aberration, is on the right. You can see the four images that I showed you in the previous slides. They're right here. So four images of the telescope beam. They look noisy. They've got speckles into it. This is actually signal. This is what we use to figure out what optical aberrations are in the beam. And on the extreme left is an image in the visible, and in the middle, that's an image in the infrared. There are actually two copies of the same image in infrared because we split the light to do polarimetry. What we were taken an image of at that time was a double star. So you can see the two stars here and there. They're separated by 0.3 arcsecond, which is about a third of the resolution of the telescope, which would not have adaptive optics. So if we turn off the adaptive optics, this whole image gets filled with light, and we can't really hope to see these two components. So this is a well-known star. It's called Sigma Ori. It's in the constellation of Orion. And you can see that even though the distance between the two stars is very small, it's so small that if we didn't have any adaptive optics, we would not have any hope of seeing the two stars. With adaptive optics, especially with extreme adaptive optics, we can very clearly separate them, even in the visible, which is considered typically more challenging for adaptive optics. We are constantly on the lookout for more efficient ways to do adaptive optics correction, especially more efficient ways to do the wavefront correction and the wavefront sensing. So I showed you, actually back a few slides. All right, I showed you this image. So this was taken with a pyramid wavefront sensor, and I'll talk a little bit later about other wavefront sensors that we're actually currently working on and deploying. A few more images that we took on sky, really highlighting the way that extreme adaptive optics gets very high performance on sky. So on the left is a video which we took on sky of a star when we have the adaptive optics system running, the extreme adaptive optics system running. And essentially what you see is a very static image of that star at the full diffraction limit of the telescope. You can see this little ring around the central spot. That is not an artifact. That is the fundamental diffraction feature of the telescope. It's called an airy ring, and it really shows that we're basically at the fundamental limit of the telescope. So we've reached the ultimate limit of the angular resolution of the telescope. You can also see these spiders diffractions. They are due to the spiders holding the secondary mirror. This image is amazingly static. If there's a planet here, if it's bright enough, we can actually start to see it. And it's a very good starting point to block the light of the star. So that's in the infrared. And in a visible, where adaptive optics is typically much harder to run, we actually still reach the diffraction limit of the telescope. So here you can see the image of star, central spot, and the ring around it. And the resolution of these images is extremely good, so we can resolve very small features. Here is an image of the star Capella that we recently took. The separation between the two stars is 36 milliarcsegons, so that's 0.036 arcsegon, which is about 30 times smaller than the smallest feature that a large telescope can resolve without adaptive optics. And we can clearly see the distance between the two stars. These stars orbit each other every 100 days, and actually from night to night we can detect that motion. And of course, what we do with the extreme adaptive optics system is high contrast imaging. So we put a coronagraph which blocks the starlight. So this is an example of an image we took. We block the starlight and we see planets around the star. So this is a star that has actually 4 planets. We're zooming in. The outer planet is outside of the field of view of this image. We're zooming in and we see these 3 inner planets very clearly and fairly easily. These planets are a few times the mass of Jupiter each. So I mentioned that we're actually developing even more sensitive ways to measure starlight, to do the wavefront sensing. So we have an ongoing development where we're actually using a different type of sensor. It's a phase diversity sensor. We basically let light propagate, and when it has aberration, that basically creates an image of the beam which has speckles, and it has modulation in intensity that we can use to recover with a computer. We can recover what is the shape of the beam, essentially the optical aberrations. So those are simulations showing that it works very well. We're in the process of building it. But here, the thing that I want to highlight is that we're trying to do the best possible reconstruction of the optical aberration with a limited number of photons, with a limited amount of light. These images on the left are actually the exact, you can see individual photons as little spots. So this is an image taken with a very faint source, and the reconstruction on the right, before and after, F is before and H is after, shows that we recover an extremely good image quality with this new type of optical sensor. And it matters because if we compare it with the current generation of sensors, so this is a comparison, this is a simulation. Top left, we have the adaptive optics is off. So this is the image we get of a star without adaptive optics. And then every one of these panels is a different construction, a different optical design for the adaptive optics system. The one at the bottom right is clearly working much better. It gives us, it concentrates the light of the star in a very small spot. And you can see this within that ring, it's very dark, which is great for looking for planets. So this is the one that we're in the process of building right now. So I want to spend the last part of the lecture to talk about very new advanced control schemes and techniques for extreme AO, things that you would not see in any conventional adaptive optics system that are unique to extreme adaptive optics. I showed the top part of this slide before. A conventional adaptive optics system takes the last measurement of the wavefront sensor, multiplies it by a matrix, and sends it to the deformable mirror. We're actually evolving to a much more powerful but complex advanced control way, where we don't use just the last measurement of the wavefront sensor, but we use multiple measurements from multiple wavefront sensors going back in time. So our best estimate of the current state of the system, the current state of the optical aberration, is not going to come from a single measurement. It's going to come from multiple measurements spanning multiple sensors, but also using the measurements, not just the last measurement, but the measurements before that, so we can sort of unroll the temporal evolution of atmospheric turbulence. So this is a scheme where we use a lot more data. We have a lot more input degrees of freedom, a lot more input measurements. And because of that, measuring the response matrix becomes actually impractical or impossible. So we actually have to learn it from the measurements themselves. So we're going into machine learning, where the adaptive optics system uses its own measurement in the history of the measurements, but also measurements across multiple sensors, to learn how to relate these measurements together in a way that creates the best possible estimate of the optical aberrations. And this is a big evolution in the way we do adaptive optics for extreme adaptive optics. One component of that is called predictive control, is one where we don't just use the last measurement, but we use the previous, for example, 10 or 20 measurements, and from the collection of this measurement, we predict what the wavefront will be in the future at the time when the correction will be applied. So our response matrix, our control matrix, which is the small matrix that we were using to go from measurement to correction, which used to be actually one of these green square, suddenly becomes much bigger because it grows an additional dimension, which is time. So here is a few of them shown here, but basically that matrix, instead of having 2 dimensions, now has 3 dimensions, and the third dimension is time. And that's been very successful. So here are some on-sky tests we did. On the left is a conventional adaptive optics system, and on the right is one where we're actually using this approach to do the prediction in the future to be exactly on time. And essentially what we find is that we gain about a factor 2.5 in contrast. So if you look, for example, in this part of the image above the black dot is where the star was, but it's been blocked. So we would be, for example, looking for a planet in this part of the image. You can see that it's about 2.5 times fainter on the right than it is on the left. So just by doing this trick where we use predictive control, we use the time information in our reconstruction, we gain a factor 2.5. And not only the image is darker, which is good for us. So it's good when we look for planets, but it's also more stable. Here is a side-by-side comparison of this time the stability of the image. I'm showing here the standard deviation. And again, it's a few times better. So that's something that we're starting to use routinely now. Another direction in which we're evolving is using the focal plane image, the image in the image of the star itself in the science camera as a source of information to get to a deeper contrast, to get better measurement of the wavefront. So this is here a technique where we look at the image where the star has been blocked. So the star would be right here, but it's been blocked. So what we're seeing is speckles, essentially a little bit of annoying residual light from the star, but it's quite faint. This is a log scale. So these speckles are 1,000 times or 10,000 times fainter than the star. And in this area that's outlined in the white shape here, we're driving an algorithm to remove light even more. And you can see it's very dark. It's fainter than 1,000,000 to 1, which means that if there was a planet that's 1,000,000 times fainter, we would see it right there without doing any processing. So this technique is working extremely well in the lab. I'm showing you a lab image here. That's actually on the instrument, but using an artificial source, a laser, and we're in the process of deploying it on sky for nighttime observation. Another variation of this is if we have a fast camera that's looking at the image in real time, we can inform the adaptive optic system. We can teach it what is, it can learn what is the best correction to do. So instead of doing this calibration step and then blindly applying it to run the adaptive optics loop, we can monitor what is the quality of the image, and we can optimize it as a function of time. So we can basically have the system learn itself how to operate in an optimal way. This is on-sky data we took recently, and this is invisible. And before we turn this algorithm on, the image is quite fuzzy, and as we turn it on, after a few iterations, the image becomes very sharp. So we use the focal plane image, the science camera, essentially the image of a star, more and more to optimize the system. We can also use the wavefront sensor information, which is shown on the left here. Again, this is our pyramid wavefront sensor, which gives us 4 images of the beam to compute what is using machine learning algorithm, neural net, to compute what should be the image based on the sensor. And this works really well. So we can actually, not only we can do a very good correction, but whatever is left, we can understand and quantify very accurately how it affects the image, and we can basically remove that effect in post-processing from our data, so we do not get confused by these errors. If we didn't have this, we would look at an image like this and say, well, maybe this little blob here is a planet. But using this algorithm, we can find out that no, it's not a planet. It comes from the optical aberrations in the beam. And so there's a lot more to it than I just showed in terms of using the focal plane image, the science image, to improve adaptive optics. So I talked about doing this control of speckles. So essentially this, I'm going back to this slide. This is what we call speckle control. Basically we control these little speckles of light to push them down, to make them very dark. And so speckle control is essentially analyzing the focal plane image, this image in the science camera, in a way so that we can actually remove those speckles and create a dark area. But we can also, from the same data, we can figure out where those speckles are and do a numerical subtraction in the computer to recover a very faint planet image. And that's an area in which we're working very actively. Related to this, we are deploying calibration schemes where we can look at parts of the image and do some analysis of this part to calibrate a darker part of the image. So if, for example, in this image, we are looking for a planet in the top square, in the top rectangle, and we use the lower rectangle as a way to inform us what is wrong with the optical beam. And we can have a control algorithm that basically uses the bright part to calibrate the dark part. And this is working very well. So this is lab data that we took. On the left, you can see before calibration, the dark part is variable. You can see these little speckles, these little blobs of light moving around. And that's very annoying because if we have a planet here, we're going to get confused. After the calibration, it's rock steady. And so this is something that is also very powerful. Again, here the theme is we're not just using a wavefront sensor, we're using the camera that takes the images of starlight itself as a way to calibrate and improve the correction. And here is some more data on that previous experiment showing that we gain about a factor of 30 in stability. So that means that we can detect planets are quite a bit fainter than if we didn't do this trick. And then my final slides are on a completely different way to measure starlight. I showed you that we use a pyramid wavefront sensor, which is putting a glass pyramid in the beam to measure starlight, but we can also build the sensor as an interferometer that essentially takes different parts of the beam and creates interferences between them. So what we measure then is fringes like this. And those fringes are actually encoding with very high precision what are the optical aberrations in the system. And that's a completely different way to measure wavefront aberrations. And that's something that we're also working on. And my final slide is about a new evolution of this scheme where we build a small interferometer where some of the outputs here in red are essentially destroyed. Starlight is destroyed, so they're very dark. That's where we'll be looking at planet. And some of the outputs shown by the green light here are used for sensing the starlight. And we combine this in a single, very compact module so that it's very stable. And then there is a very good relationship between the green signals and the red one. And so we use the green ones as the input wavefront sensing to keep the red ones as dark as possible. And then we look for planets in these red signals, in these red traces. And the color, the wavelength is going along the x-axis. So we also get a spectra of whatever planet may be revealed. So if a planet shows up, for example, if there was a planet, for example, we would see this line lit up, and we would measure the colors of the planet. So that's my last slide. I think I gave you a fairly technical but broad overview of what we're doing right now with extreme adaptive optics, but also what's coming and what are the main areas of development. Thank you.
Well, thank you. That was great. And I feel like we need about 5 more lectures to get more information and understand more completely how the systems work. So let's start with a question from John Mather, probably known to everybody. John, can you turn your mic on and ask your question?
Yeah, does this work?
Yes.
Yeah. Yes. Hi, Olivier. Just wanted to know, how far do you think we can get with all of these new advances in techniques and methods? Say for a really bright star like Alpha Centauri or something nearby.
Yeah, hi John, great question. Definitely something that's on our mind on a daily basis, I would say. We think we can get to about a contrast of 10 to the 8 from the ground with large telescopes on the sort of 30-meter class. So the upcoming telescopes, we think we should be able to reliably image planets down to 10 to the -8 contrast. What that means in terms of science is that we will not be able to image planets exactly like Earth around stars like the sun. That has to be done from space, at least not in optical or near-infrared light. However, that means that we should be able to image Earth-like planets around cooler stars, the so-called M-type stars, which are at the contrast level of 10 to the 7 to 10 to the 8. As a benchmark on the smaller telescopes, on the sort of 8-meter class telescopes today, we are reaching about 10 to the 6 contrast. So the improvements that I showed in techniques will give us about a factor 10, and this is slowly already happening. And then the larger telescope gives us another factor 10, but more importantly, the larger telescope also gets us to work closer into the stars, which gives us access to habitable planets around these nearby, what we call M-type stars. So I hope I answered your question. I should conclude by saying that you should ask me this question in a few years, and maybe I'll have a different answer. We keep struggling with what is the fundamental limit, because we keep, in a good way, we keep having new ideas and pushing the envelope. But it does look like going beyond 10 to the -8 is exponentially hard.
I have a follow-up question. How does that compare to what you can do in space?
So in space, you can go. You don't have the atmosphere to deal with.
But you
it becomes an engineering challenge. But in space, you can go deeper. You can go. So the contrast limit is if you build the telescopes very carefully and keep things very stable, you can go to 10 to the 9, 10 to the 10. So in space, you essentially very quickly hit another limit, which is the photon noise limit. So you're not limited so much by contrast, but by basically how much light comes from the planet. So on the ground, we have access to much larger telescopes, or we're mostly limited by how much light of the star is left on top of the planet, because that's what's hard to push down. In space, you can do a very good job at this, and then you get to the limit where you're limited by how much light you get from the planet. And then there is, so in space, what really pays off is if you build a large telescope in space with a coronagraph, because then you can go very deep in contrast, and you have enough collecting area to make use of that. On the ground, it's a combination of, we're mostly limited by how much starlight is left on top of the planet. We have access to much larger telescopes on the ground. The two are actually highly complementary. It's in optical light, the space is going to be quite a bit better, because that's also what's hard for adaptive optics on the ground. And in near-infrared light and infrared light, the ground is more capable, just because we have access to larger telescopes.
We have a question from Ron Eckers. Ron, can you turn on your mic and ask your question?
Okay, and hi Olivier, this is Ron Eckers from Sydney in Australia. Thank you. I noticed that the Fresnel diffraction rings are quite clear in many of your images. That, of course, is coming from the sharp outer edge of your circular aperture. Would you get an advantage for planets in those regions if you apodized the aperture or had an irregular and not a sharp edge?
Yes, absolutely. So this is the chronography part of our systems, which I did not describe very much. But there's a whole second layer after we get this diffraction limited image with these diffraction rings, these Fresnel rings. There's a second layer of the instrument that removes that. The technique you mentioned, the apodization technique, is one way to do this, and we have multiple ways to do this. Essentially, they're using chronograph masks to block, not just to physically block the light of the star, but to cancel these rings. And there's a whole field of research into the optimization of these things. And I would mention that the very last slide I showed is also a different way to achieve the same result, using destructive interference in essentially a mini interferometer that achieves the same cancellation of unwanted starlight.
Okay, we have a question from Frederica Durema. Frederica, you want to turn on your mic and ask a question?
Yes, thank you. Thank you, Olivier, again for a very nice presentation and talking actually about the details and showing what the challenges are. My question, it was originally for your first part where you talked about the wavefront sensor response to the deformable mirror commands is linear, and I kind of asked, it's not really linear, and then but then you talked about the predictive control and sensor fusion, so that supersedes that's more simplifying original assumption. And then, of course, I had several of the questions that were asked. So in terms of, and you talked about complementarity between, ground-based telescopes and space. So how this complementarity will be exploited to understand more detailed characteristics about these exoplanets, to compare them, for example, with respect to the Earth, or what the differences would be, and so on.
Yes, so I'll briefly comment on the first sort of question/comment. The reason wavefront sensors are linear is actually mostly because we built them that way because we didn't have computers that could deal with non-linear wavefront sensors. So historically, we've actually gone into great pains to make our wavefront sensors linear so that we can use relatively simple algorithm and computers to drive the AO loop. It turns out that that's not the right way to do things because that forces us into adopting solutions that are not optimal. And so I alluded to that in the presentation, and that's definitely a direction in which things are evolving because we have better algorithms and computers. In terms of space and ground complementarity, there are two dimensions to it. One of them is the wavelength dimension, which is that generally speaking, the ground for exoplanets that are close to stars, the ground is going to be better for infrared. This may be surprising because some of you probably know that when astronomers talk about infrared, they say, well, you need to go to space because there's no background. You go to space because there's no background when you look for faint galaxies. When you look for planets that are very close to stars, you have another problem, which is that the diffraction limit of the telescope gets too big if you go to long wavelength. So that's why you want to use the largest possible telescopes, which happen to be underground. So there's a wavelength complementarity where in optical light, definitely space is going to be the way to go. And in infrared light, especially looking at young planets that are still quite luminous, self-luminous from their thermal emission, but we want to go very close in and we need large telescope, the ground is going to be the place to work. There's another dimension to it. It's what types of stars we're going to be looking for planets around. So those two things are coupled. If we look at a sun-like star with an Earth-like planet around a sun-like star, we're going to have to do this from space because the contrast between the planet and the star is on the order of 1 billion to 1 or 10 billion to 1, and we don't think we can do that from the ground. Now, if we look at habitable planets, Earth-like planets, in thermal emissions, so at 10 micron, we can do that from the ground, not super efficiently, but the contrast then is only 1 million to 1, and we can do that on the ground. Or if we look at planets that are around M-type stars, cool stars, the contrast is not that challenging. It's maybe 10 million to 1, and we can do that from the ground. I'm talking here about habitable planet, Earth-like planets.
Right. Thank you.
So while we're on that subject, let me ask you to contrast what you're doing with what the Webb will be able to do. They're obviously very different, but the Webb is also going to be looking for exoplanets and trying to.
The Webb telescope is going to be the prime telescope to do for really two types of measurement. One of them is the transit measurement, the transit spectroscopy. So for habitable planets, Webb is going to be looking at hopefully transiting planets. So the challenge there is where to look and at the right time. But if an Earth-like planet transits a low mass stars, the Webb telescope can take a spectra of the starlight going through the atmosphere of the planet, and can do that in near infrared and infrared with a sensitivity and especially a stability that we cannot get from the ground. So that's one aspect. That's one way that Webb is really going to be extremely powerful for exoplanet. The other one is related to planets that are young and at quite large angular separation from their star. Webb is going to be extremely sensitive in infrared, much more so than any ground-based telescopes in terms of being able to detect very faint sources. So it will be able to image these planets, these other planets, with direct images in the infrared. Where the ground is going to be the best is really for the inner planets, where you need a very large telescope and also potentially at shorter wavelength than what Webb will operate at.
Ron Eckers has another question from Australia. Sorry, Ron.
Okay, Sorry, Larry, I didn't put my hand down. But I could easily ask another question. I noticed there's more overlap, I think, than there used to be between your extreme adaptive optics and the techniques used in adaptive optics, deconvolution in radio astronomy. So my question relates to your last point about starting to use interference. Is it possible to get close to recording, perhaps in the infrared or submillimeter in real time, the actual wavefront information? So you don't have to make a correction in real time, but you can do it later as we do in the radio.
So that's a very interesting question. I will admit I don't know the answer. I've been curious about that as well. So there is one reason that pushes us to do things in real time, and it's the photon noise, the shot noise. We do need to optically cancel before we take a measurement as much as possible. So that does push us in the having to do things in real time and not being able to not being able to just rely on post-processing or real-time recording of the complex amplitude itself. In terms of no, that doesn't mean that won't be useful. At the short wavelength, there are significant technological challenges in doing what you're suggesting, which is basically a real-time recording of essentially complex amplitude of electric field, and so that really hasn't sort of gotten onto our radar yet. But yeah, it's a very very intriguing possibility for the future.
Thank you.
So I'm curious, how do you make your actuators? Are they micro, fabricated?
There are different ways. One way is to use piezoelectric material. Piezoelectrics basically convert an electric voltage into a displacement, into a contraction. So we actually have mirrors that are made out of this material with electrodes etched onto them, so they can bend and deform at high speed. So that's one technique. Another technique is to use magnetic force. So basically tiny little magnets with tiny little voice coils. You attach one of the two to a mirror, the other one to a structure plate, and if you make them small enough and light enough, they can move fast. And then another technique that is used is using the electrostatic force. So actually, our fastest mirror in the system that I presented uses that technique. It's very compact, and each actuator is so the mirror itself is about 20 millimeters across, and it's got 2,000 actuators, and each of them is essentially a little capacitor, but the top plate of the capacitor is flexible. So as you put an electric voltage across the capacitor, the top plate gets attracted to the bottom plate, and it collapses a little bit. And you attach that, you build an array of those, and you attach them to a continuous mirror.
So these are done by photolithographic kinds of and
yes, that last
techniques.
yes, yeah. So actually, that last technique is technically what we call micro machines, which are mechanical devices that are done by etching technologies.
Yeah, that's what I was wondering. I don't see any other way to do it, but I thought I'd ask. We have a question from Jennifer Weissman on YouTube, which I have to read to you. Hi, Oliver. The National Academy has released its decadal survey recommendations for the next decade of astronomy. Are the technologies and techniques you are working on discussed in the decadal report?
Yes, very much so. So the decadal report really realized and documented that one of the key science goals, actually maybe the most prominent science goal that was outlined for the next generation of large telescopes, both ground and space, is exoplanet imaging. there is also recognition that we need further technology development to realize some of our dreams in that area. This is exactly what I was talking about today, the things we're doing and testing, both in the lab and on sky. But this was very prominently featured. Our community has been very excited to see this in the report, and it's very encouraging. And it also is very timely because this is at a time when the next decade we will be building or at least either building, commissioning, or designing the next generation of large telescopes, both in the ground and in space. And so the instrument technology that goes behind that is also very much in motion.
There was one thing in the talk, well, probably more than one thing, but one question. You didn't say anything about laser guide stars. And
yes, very good comment. We actually typically do not use laser guide stars because we have a bright star exactly on axis, exactly where we need to look at. I'm going to give you the sort of conventional answer and then my take on this. But the conventional answer is extreme adaptive optic systems don't need laser guide stars. Because there's a bright star on axis. Now, it's not entirely true, and one thing that's potentially interesting is if you have laser guide stars that are slightly off axis, you can see turbulence before it hits the beam, before the wind moves it into the beam, and so you can get better performance if you actually leverage that. So you can have essentially a multi-laser guide star systems that does a tomographic reconstruction of the atmosphere above you and can see the atmosphere before it enters your beam. So it gives you an edge essentially in the correction. Now there's another different aspect of this is that if you and it's not really a laser guide star, but there's been studies of satellite-based guide stars. So you fly a satellite that shines a laser back at your telescope to essentially give you a star that's even brighter than the star you're looking at, which would be very useful because, as I mentioned, we never have quite enough photons to make the measurements we want. And then the challenge is completely different. It's how do you keep it aligned for long enough, precisely enough, so that it's practically useful.
Is this predictive correction the reason that the EELT, the European Large Telescope, has multiple guide star capability? So I think they're built with 4 or 5 lasers.
Yeah. So the reason that laser guide star adaptive optics system use multiple guide stars, there are 2 reasons. One reason is that if you only use one, if you trace the light from the laser spot to the telescope, it's a cone, and so the side of the cones are parts where starlight will go through, but you don't measure them. So there's a mismatch basically between the starlight from infinity, which is a cylinder, and the cone, which is coming from your laser guide star, which is at a finite distance. And so what to get this missing part back, one approach is to have multiple laser guide stars so you cover the whole cylinder. And it's called laser tomographic adaptive optic systems. Another motivation to have multiple stars, guide stars, laser guide stars, is to increase the field of view. So you not only you measure the sort of cylinder of turbulence from a point at infinity to your telescope aperture, but you can do it from a range of angles on the sky. And so those are the reasons that that colleagues that do wide field astronomy basically build systems with multiple laser guide stars. Now I'm coming in and I'm saying, well, maybe I can use that for extremeo for predictive control, but that's not why they built it.
That's not why they're doing it. Doesn't that make it a lot harder to do the proper deformations on the mirror? There's only one deformable mirror, I think, in the EELT.
Yeah, so that's right. Well, it depends on the instrument modes, and telescopes that want to do wide field adaptive optics, they need multiple DMs. They have to have, there's no way around it. One single mirror cannot do it all. So they build Sometimes they use one DM that's part of the telescope, and then they add several other DMs in their instrument to correct multiple parts of the field. And there's various ways to do that optically. But for the laser tomographic application, where the goal of having multiple lasers is not to increase the field of view, but to have a better knowledge of the turbulence for a single direction, you only need one mirror. You need multiple sensors, but one mirror for that second application.
I don't think there are any more questions. And I don't think I should monopolize the questioning. So let me thank you so much for coming again. It was a really interesting talk, and I love the pictures of your instrument because I can't be there in person to see it. And I learned a lot, and again, thank you so much. And hopefully you'll come back when it's all working and show us what results you're getting. If I could twist your arm to do that at some point in the future.
Thank you.
Our next talk will be on Jan 28th. Our speaker will be Ray Lugo to deliver the 2453rd lecture. Ray is CEO and principal investigator of the Center for the Advancement of Science and Space, which is the organization tasked with certain aspects of managing the U.S. National Laboratory, that is the International Space Station. And Ray will be discussing principally the Center for the Advancement of Science and Space and what it does. We hope this meeting will be in person, but ultimately that will be determined based on COVID and the COVID-related measures in place at the time. The 2454th meeting will be on February 11th, 2022. The speaker will be Roberto Tamai, who is the program manager for the European Southern Observatory's extremely large telescope project that we mentioned tonight. He will be speaking about design, engineering, construction, and capabilities of the ESO-ELT. This will be the final lecture on the 3 very large Earth-based telescope projects currently planned and under construction, and including the 2 complementary lectures on adaptive optics technologies that make it possible for these observatories to see almost as well on Earth as they would in orbit or further out in space. Roberto is based in Europe, and he will not be joining us here in DC. So the event and the lecture will be done via Zoom, as was done for tonight's lecture. Please check the PSW website often, www.pswscience.org, for up-to-date information on meetings and whether lectures will be in person or via Zoom. COVID and COVID-related public health measures are constantly changing, and PSW is adjusting plans accordingly. But we ask you to join us for these meetings, whether by Zoom or in person. And finally, let's thank tonight's crew, Robin Taylor, James Hewlin, and McQueen for helping produce tonight's meeting. And with that, I bid everyone a good morning, a good evening, a good afternoon, or a good night, wherever you happen to be. And I thank you all for joining us. And I will adjourn the meeting now to wherever you're going to do next. The meeting is adjourned.